So we're talking a bit more about prior and posterior distributions, how to work with them. So you're going to the last lecture, or a couple of slides to the last lecture, and then move on. We have our statistical model, where we have a deterministic and a stochastic part. This defines my statistical model, right? So the deterministic part, maybe this is the linear regression part, and I have to specify somehow how I think the actual data is distributed around my mean prediction, and this defines the statistical model. And for these parameters, I can derive a formula for posterior distribution of my parameters once I have seen the data. You can think of it as like, because it is prior times likelihood, you can think of it as like, you have some, maybe some information about your parameter, that's the prior, and you update this by the information of the data, which is the likelihood function. And then you can make quantitative statements on your research hypothesis. However, we don't have access to this function itself, but we can sample from it by MCMC. So yeah, you should think about, okay, what is my response? For instance, is my response continuous or is it discrete? This should lead you in the decision in how do I choose my likelihood function? How should the response be, or how is the response distributed? Right, so we can have discrete or continuous distributions here for the response, which then define the likelihood. However, the likelihood is a function of the parameter. So in all of our cases, all the parameters here are continuous. We are not using discrete parameters here. So the likelihood function will always be a continuous function, even if the data is discretely distributed. And therefore, for the prior distribution, at least here in all our examples, as a prior distribution, you will always choose a continuous distribution, right? Because the parameter itself will be continuous. There are, I would say, just a couple of relevant prior distributions or families which we are using here. Here you should just think about, okay, is my parameter, has it to be strictly positive, or can it be kind of any value, negative or positive? Here in this case, we had a special case that the parameter itself is an average survival rate, so it should be bounded between 0 and 1. And here classically, the beta distribution is a choice for the parameter which is bounded. Then the likelihood function, this comes directly from the model. Once you defined your kind of deterministic, for instance, the linear model, here it was just fitting an intercept. And the stochastic part, this is the kind of, how do you think the data is distributed around the mean prediction. This defines the likelihood function. And the likelihood function of a parameter is a product over all likelihood functions of all the data points. Then the posterior distribution, we will not have access to the nice kind of curve of this posterior distributions because we just don't know it. I mean, we talked yesterday about why this is not possible. However, we can always use sampling by just exploiting this property here that it is proportional to prior times likelihood. So all the information is just contained in a long list of values for the parameter. And you can, for instance, draw the empirical histogram here. So we do not actually need to save these values of prior and likelihood or prior times likelihood. I think BMS does save them for some other reasons, but you do not need them for making any statistical inference. All the information is contained in the samples themselves. And this makes it very easy to do all kinds of statistics, because basically everything downstream from there, you just have to count. There are some nice tools to help you find some distribution. I'm just showing you one or two of them. Yeah, for instance, yeah, continuous distribution, for instance, normal, and then you can kind of play around with the parameters and see what happens. Right, so the normal distribution is not bounded, but maybe you are interested in a distribution which is bounded at 0, and there the gamma distribution can be a choice. Right, so here it is bounded at 0, and it has some parameters. This is sometimes a good choice, or the exponential function. That's a function, again, it is bounded at 0 and just has one parameter. There's another tool that gives you a bit of more information, but you can also play around with this if you want to. But in general, there's often only a couple of in practice, just a couple of distributions you need to kind of know for choosing priors. Okay, so let's talk about prior distributions. So we said they represent my belief about the model parameter. And classically, I mean, that's the way I learned it in the course, that the instructor said we should write down the prior before we go and observe the data. That's a very old school interpretation, I would say, because often you don't have this information or exact information. In the literature, they always say, oh yeah, just look at some previous experiments or related studies. However, in ecology, often we do not have the luxury to have these experiments because we are the first ones to perform them. And therefore, this kind of very general recommendation often don't apply. But there's a more modern viewpoint that you can use prior predictive checks. And this is fitting the model just by sampling from the prior and comparing model predictions then with the data. And this will give you an idea if the priors make sense. Because if the priors make predictions which are way off, I don't know, orders of magnitude different from your parameters, this might not be a good choice for the prior at all. And the last point which I want to make is priors are problem specific. This means whenever you change something in your, for instance, in your model or in your scaling, the prior changes. You can't use the same prior if you, for instance, scale your predictor or you scale your response, then the prior also has to be adapted accordingly. I would say there's generally 3 types of priors, but there is no formal definition of these. I would say the first is either completely flat or an uninformative prior. This means you know nothing about the parameter, but I would argue that this is really rarely the case. Specifying a flat prior in BRMS is just, you don't specify a prior for this specific parameter, then automatically it's a flat prior. So if you do not add this information in BRMS, you're not using any prior, with the exception of the intercept and the standard deviation, which always have the default prior in BRMS. I would say often you have at least some idea about the parameter, for instance, at least the order of magnitude. You often know if your kind of effect size or your slope will be, I don't know, between 1 or 2 or between like 5,000 and 10,000. And especially if you scale all your data, right? Scale everything to 0 mean and standard deviation of 1, then you already know that the slope of, let's say, 100 is completely improbable. So you could kind of use priors that reflect the scale of your data. And finally, well, sometimes we're in a lucky situation that we have an experiment or we have experience where we actually can put in informative priors, for instance, from a different data set. So let's see how the choice of the prior affects the posterior distribution. So here the red line is just some curve of some likelihood function. Here again the case, the survival rate, just one data point. Down here on the x-axis, you see the mean. I think that's the mode. Yeah, I think it's the mode of the distribution. So where the maximum is reached. So if you wouldn't have any prior and you would do maximum likelihood optimization, the red one would be the estimate. So this is the maximum likelihood estimate, because here the likelihood of the data is maximized for this choice of the parameter. And then having different priors, they all have the same mean, 0.5, but they have a different level of information. So the concentration towards the mean increases from flat to weakly to highly informative. And you see how, in this case, the posterior mean estimate, so the purple one here, is drawn towards the mean of the prior. So for flat priors, the posterior is proportional to the likelihood, and we can turn the likelihood function into a probability distribution, or at least we can sample from it. And for any other choice, the posterior will be some compromise between a prior and likelihood. So the prior is my information which I have before evaluating the data, and the likelihood is the pure information that the data brings into the model. So for weakly informative priors, for instance, this one here, the second is very weakly informative. Just one data point here can draw the posterior towards the likelihood. However, for more informative priors, you would need more information from the data to overcome your initial belief, which is encoded in the prior. But also the likelihood affects posterior. So now it's a different way around. Here the prior is the same for all of them. We have a weakly informative prior with a mean of 0.5. And each of these panels has a different number of observations. And often or generally with a number of observations, the width of the likelihood shrinks. Right. So here in this case, the more data points you have, the more information, the more certain you will be about the estimated parameter. And if you have many data points, the posterior will be dominated by the likelihood information and not so much by the prior anymore. So for small data sets, the prior usually dominates the posterior. But I mean, small data sets is very small data sets here, just 1 or 2 observations. Whereas for large data sets, usually the likelihood has the strongest influence on the posterior. And also the width of the posterior shrinks. The standard deviation of the estimate also shrinks. That means also more certainty about your parameter. Yeah, often I often hear the questions if priors are subjective. And so here, the likelihood, the maximum likelihood function is kind of giving you the same answer. It's purely driven by the data. So you could say, okay, well, priors are purely subjective. Why are we doing this? And I would say, first of all, not including any information is also a choice that you are doing, right? If you say, okay, I'm completely blind towards the data, towards the results, I just let it purely be informed by the likelihood and by the data points. This is also a conscious choice you're doing. Because usually you do have some idea about the relationship. For instance, if the relationship should be positive. And the posterior is some kind of compromise between evidence from the data and your general reasoning. And yeah, if you have previous results, this should go into your analysis, right? So it would be a waste to throw this information away. Then a very general comment, I say nothing here is purely objective, right? We think of, okay, if I fit the model, this is purely objective. But in collecting the data, many kind of non-objective choices have been gone into this research anyway, right? Choices about how to select the data, what to observe, and so on, and so on, and so on. So don't be fooled to say that, well, frequency statistics is purely objective. A lot of kind of non-objective choices have gone into collecting the data already. And sometimes you need them, especially in complex models. You have to limit the choice of the parameters a bit to actually get results in the first place. And if you're still worried, you can always fit the same model with a different choice of priors and see if this changes the results a lot. And yeah, quite modern view of change or of choosing priors is prior predictive checks. And this is a way of comparing what you expect the priors or what you expect from the priors to the data. That's a bit often a bit controversial because you say, okay, the prior information is your belief and the data information is in a likelihood. So why should you let the data inform your priors as well? But I would say if you use completely uninformative priors or priors with a very wide standard deviation, then the priors already can make predictions which are completely nonsense. If we look at this example, especially if we have something on a log scale, here classical predator-prey body size relationship. And if we here just have a prior which has, I don't know which, but I think it's maybe something with a standard deviation of about 10, maybe 20, I don't know. No, I think it's 10. Standard deviation of 10 and a zero mean for your slope, and you simulate data from your prior, you get this insane results that body size relationships are predicted for large animals eating something which is larger than the Earth. So this doesn't make any sense at all. So you know these kind of choices for the prior, you can easily kind of narrow it down to more reasonable values. And here, I guess to limit this to maybe a choice with a zero mean or even positive mean and a smaller standard deviation of 1 or 2 makes predictions which are much more in line with reality. I mean, we still get some negative values here, but right, so negative predator-prey relationships, but at least the order of magnitude is correct here. This might be especially useful if you have like transformations like log, or if you use GLMs, where internally transformations through the link functions like logit are used. So there it often makes sense to just check what the priors, or what the range of the priors, what kind of predictions you can make from that. And you can very easily do this in BRMS by just fitting the model and specifying sample prior only. Then the model ignores the likelihood function and only kind of samples from the prior, and then you can make predictions from this and compare the predictions to the data. Okay, yeah, I'm quite happy about this. This is more widely accepted, for instance, in Richard McElrea's book, Statistical Rethinking, that prior predictive checks nowadays are much more accepted. We have seen yesterday already, or also this table, we've seen it already, that BRMS automatically chooses some priors for intercepts and standard deviations, so we don't usually have to take care of this. It is already kind of based on the observed data. However, the intercept is based on a mean-centered predictor. So it means the intercept for some mean data point, and it so the prior is chosen for this mean kind of intercept, and not for the intercept where x is equal to 0. So my advice is just to not touch the intercept prior unless you have a specific reason for it. However, you should use, or you can and should use priors for the effect sizes, and you have to choose them on your own. Okay, so now we are having a closer look at the posterior distribution and what we can do with it. And the first thing I want you to never forget is that the posterior sample, it's a multivariate sample. If you just have one parameter, you don't have to think about it, but usually you have more than one parameter. For instance, the classical linear regression has 3 parameters: intercept, slope, and standard deviation of the residual. So the output, or you can convert the output just to a matrix or data frame. In this case, every column contains all the samples of one parameter, and each row contains one sample of all the parameters, and they are connected. So this means that each row corresponds to one point here in the samples. Right, so this is one of these many dots here, and this one is this here. However, this is not part of the posterior sample. You cannot just have some random entry from the first column and some other entry of the second column. This is just not part of the posterior. This kind of combination has not been sampled. Only kind of each row has been sampled. So each sample is a multivariate object. And once we have this kind of collection of samples, everything I compute from them, and this is basically everything connected with statistical inference, will also have a distribution. What can I do with a sample of the parameters? Right, so this is a sample of or the distribution of samples of the parameters. What can I do with it? Well, I can make a prediction for a certain data point. It will be a distribution, because with each of the sample you can make a prediction, and then you have this collection of predictions, which is a distribution. For hypotheses, you will have a distribution. You will have a probability distribution associated to your hypothesis. Post-hoc analysis, or for instance, comparison between groups, you will get a distribution here. So you will get a distribution of the difference in groups. which you can use to assign probabilities to it. Also, the model fit is a distribution. It's not that important here. However, the R² value, for instance, it is calculated from the predictions. The predictions are distributions, so also the R² value is a distribution. And also model comparison will be associated with some uncertainty. However, there the connection is not that easy that from the samples of parameters you get a sample of ARC values, but I won't go into that detail now. Just think of everything you calculate after model fitting will be a distribution. So let's look at predictions. We're having this example here. It's a simple linear regression. I think there's a linear relationship between weight and age for individuals of the species, and the residuals are normally distributed. I have 3 parameters: intercept, slope, and standard deviation. So I fit the model and I look at the summary. Then I get some estimates for the mean of the posterior distribution for the intercept, and also the mean of the posterior distribution of the slope in age. And the third parameter is down here. That's the mean estimate for sigma. And they are also associated with some standard error. So this is the standard deviation of the posterior for each single parameter. However, we should not use them for making predictions. This is definitely different to frequentist statistics, where you usually use them for making predictions. Here, this is handled a bit differently. So we have mean values for the intercept and mean value for slope, but we do not use these mean values for making predictions. We can do better. We can use the whole posterior distribution to make predictions and then quantify the uncertainty of the predictions accurately. So let's look at our posterior sample again. Right, so let's forget about the mean intercept and the mean slope for now. We have intercept in form of samples and also slope in form of samples. And this means for each row here, I can make a prediction. Let's say, okay, I want to predict at age equal 10.5. So I have my predictor value. So here for this age, 10.5, I want to make a prediction. Then for each sample of the posterior, I can make this prediction. It's just intercept plus slope times age, and I get a value. And I can do this for all of them, and I get a distribution of values here. And this will define my distribution of my fitted values at age 10.5. Note that this is only using the deterministic part so far. So it's just a distribution of the mean regression line, just the deterministic part. So each sample from the posterior generates one sample for the prediction. And I can plot the histogram for these predictions. And you can use this either the command fitted or the command posterior epred. This is for, I think, expected prediction by specifying some predictor values, and then you will get these values here, and you can look at the histogram. So this was just for one data point, so for age equal 10.5. However, we can also, for each line of each row of the posterior, we can draw the whole regression line here. Right, so this already defines the whole regression line. It has an intercept, it has a slope. So this defines one regression line. And the second one defines a different regression line, and so on. And if I look at the 10 first samples, they define 10 different regression lines. And if I kind of do this for maybe 1,000 samples, I get this whole distribution, which I can, for instance, if I slice through at a certain age, for instance, here at age 10.5, I get the same distribution as before. So this is my distribution of fitted values. And you can extract confidence intervals here, or we call them credible intervals. For instance, with a conditional effects plot here. So this is just the 95% quantiles here of these fitted values. And the mean line here, this is the mean regression line. Right, so for each kind of each point on the x-axis, we're making a slice here and plot the mean and plot their quantiles, and then we arrive, if we connect them, we arrive at this classical shaped credible intervals. Classically, you would plot 95% credible intervals, but it's no problem using different values for the intervals. With this method, you will always get the correct quantification of the uncertainty. We'll get the correct credible intervals for each, for any level of certainty you're choosing. Okay, so this is, or this was the fitted distribution, right? It describes the distribution of the mean fitted value, and it only uses the deterministic part of the model. In this case, just the regression line. However, the model contains another part, and this is the stochastic part. And we can also include the stochastic part here. And I'm adding this other parameter here, sigma, because sigma is only a parameter of the stochastic part of the model. So for each line here, we can compute the fitted value. Right, so this is one predicted or one fitted value for h is equal to 10.5. And we can draw a random data point now because we know the sigma, we know the standard deviation of the residuals. So we can draw a random, or we can kind of simulate a data point by using this mean prediction and drawing from the normal distribution, because this is part of the model, right? If we would choose another distribution in the model, we would have to use another distribution here. So we randomly generate data points here from this part. So the mu here, that's the deterministic part, and we additionally put in the variation of the residuals. And then we get something which is wider than just the fitted distribution. And we usually call this the predictive distribution. So the fitted distribution is just on the level of the deterministic prediction, whereas the predicted distribution is on the level and the range of the actual observed data. And you can also use this in the conditional effects plot by specifying method is equal to posterior predict. So the posterior prediction is always prediction on the level of the data. It includes the deterministic and the stochastic model part. And since it involves a bit more stochasticity than just the deterministic part, the quantiles here can look a little bit like wiggly, but that's totally normal. Usually, most of the data parts should be in this prediction intervals. And if you have like 100 data points, you can expect that maybe 5 of your data points will be outside your 95% prediction intervals, and 95 of your data on average will be inside the 95% prediction intervals. However, since there's just a few data points here in the simple example, they are all in the 95 prediction intervals here. Okay, why are we doing this? Fitted distribution and predictive distribution. We can, first of all, we can use this to visualize the model, to see, to visualize here this positive relationship. But we can also use this to check if this is actually a good model. So the next part would be predictive checks. What can we do with this model predictions? So Bayesian statistics does not free you from model assumptions. So I wrote the classical model assumptions of linear modeling. So you assume that the observations are independent. The trend follows the linear prediction model. Right, so you choose the right kind of model class, or to describe your data. The residuals should follow a normal distribution. Normal distribution is the classical choice, or the definition, or it's defined as normal in a linear model. And also constant variance. However, this information is already contained in the third one here. The sigma here is a constant. The variation does not increase along values of the x-axis or values on the y-axis. And we can use model predictions to check these assumptions. First of all, the conditional effects plot. This is super informative. If you have one predictor, if you have more than one predictor, you can still plot these, but you know that the fitted line here will not always kind of explain everything in the data well, because you can only plot against one predictor. However, there's a way which is of plotting the data and predictions independent of the number of predictors. And this is plotting the data against the prediction. Right, so here you're plotting, that's the response and that's the predictor. And you're plotting both data and the predictions in this plot here. Here this is different. Both of the axes contain values of the response. But here on the y-axis, this is the observed response, the data response. And on the x-axis here, this is the predicted response from the model. And if both of them are concentrated along this diagonal, then observed and predicted values match up quite nicely. And the posterior predictive check function has different types of presentation. Here, the scatter average gives you this classical observed versus predicted plot. And it's a function from the brms package. I guess usually you know this one also from frequentist statistics. Then here's another plot which I mean it's not necessarily connected to Bayesian statistics, but it's become more popular nowadays. I see it also in frequentist statistics, and it's also a nice tool to see if your predictions match up the data. And this is a density plot, or you can think of it as a histogram. First, the dark blue line. This is just plotting a histogram of the observed response values in the data. So here you have, I think, that's kilogram or its weight on the x-axis. So that's a distribution of the observed weights in your population in the data set. And now each light blue line is one replicated data set. So each line is the histogram of one replicated data set from the model. And then you repeat this, because for each sample you can replicate a data set. For instance, here with 50 samples, you generate 50 data sets, and then you get 50 lines, and you look if they kind of match up nicely. Then since recently, there is this performance package, which is quite useful. Again, this is not necessarily connected to Bayesian statistics. It's used in the whole linear mixed effects model framework as well in the frequentist world. And it also gives you, it works together with the BRMS package, and it will give you some nice plots for model checking. So the first one just plots the fitted values against the residuals, and it allows you to see if the kind of the spread of the residuals increases. And here, this mean green line here should be approximately constant. Here, that's the same information displayed a bit differently. So here the residuals can be either positive or negative. So this is the raw residuals. Here, it is the absolute value of the residuals. So they're all positive, and they're also square root transformed. And if you see here a positive or negative trend, you know that the residuals do not have the same or constant variance across the whole range, and this would hint to not having constant residuals. Then the next two, this is basically the well-known QQ plot. So it plots quantiles of the residuals versus quantiles of standard normal distribution. Usually, you can also plot it that they are along a diagonal. Here they are kind of shifted, that they should just be concentrated around zero along the zero line. But this is just a rotation of your classical QQ plot. And here, this is the same information as this, also displayed a bit differently. So that's a distribution of the residuals versus the standard normal distribution. And they should kind of look similarly. And then this tells you that the model assumption of normality of residuals is fine. So these all work with LM, but also with the classic with the BRMS package now. So I think this is pretty useful there. Okay, so there are two things that you can do wrong with the posterior, and basically both of them are connected to using mean predictor values for predictions. Mean parameter values for predictions. So look at this figure here. That's the beautiful country of Croatia in southern Eastern Europe, and it has this weird shape. So the geographical center of Croatia is not even located in Croatia. So it's located in a different country. So it's not part of Croatia at all. And if you think of this would be your posterior, and you are using the mean values of, for instance, longitude and latitude, so this would here be parameter A and parameter B, then this mean wouldn't be part of the posterior at all. This special combination of parameters, A and B, would have zero probability mass. So it's highly unlikely, and making predictions with this highly unlikely parameter combination is completely meaningless. So always use the full posterior for making predictions. Do not just extract mean values and do further analysis with these mean values. You have access to this whole range of uncertainty. It's all correctly quantified in the MCMC, so you can use that. And fortunately, the BRMS package automates a lot of these. So you don't have to make predictions yourself and do stuff with it. You usually can just work with functions from the BRMS package to work with that. Second, again, connected with the mean parameter values, but for different reasons. And this is for nonlinear models. So often, if your posterior does not look like this, if the posterior looks nicely and you have a linear model, then the mean of all the predictions is the same as the prediction with the mean parameter value. But only if you have a linear model and your posterior looks nicely. In other cases, for instance, GLM, you will make predictions that are wrong if you use the mean parameter values. And this is because usually they have, at some point, there's some nonlinearity, for instance, the link function, so the log or the logit. And in general, for nonlinear functions, we have this property. So look at this black curve. This is an exponential function, so it is nonlinear. And you have two values, θ1 and θ2. And you can make a prediction, or you can, make a prediction with this parameter 1. This is mu1, and a prediction with this parameter 2 is mu2. And then you can calculate the mean. And this mu bar here, this blue one, that's the correct mean of the predictions. However, if you make a prediction with a mean parameter value, you will get some other whatever value, which is not the same as the mean predicted value. So these are different. It's called Jensen's inequality. It appears quite often in ecology. There's a couple of papers about it. So again, please always use the four posterior for making predictions. Just to end this lecture, we have a prior distribution, which usually you have to choose. But in general, I would say that the choices of distributions, you can always do something with a normal distribution, or maybe some other distributions if your parameters are strictly bounded, for instance, positive. The likelihood function, here, it all depends on your data, right? So you can have discrete or continuous likelihood, continuous or discrete distribution of the data. However, they will always produce a likelihood function which is continuous if you have continuous parameters. So this is usually not critical. This will come from the structure of your data. The posterior, you will only have access to this in form of samples. So first, before doing any analysis, you always have to check the convergence of your MCMC. Then, often people are worried about priors if they chose them correctly. But often, I mean, if you have a large data set, then the choice of the priors is often not that important, or it's not very sensitive. However, if you just have a few data points, you actually want to put in some information, because the just a few data points will just not give you good evidence for your parameters. So sometimes you, especially with small data sets, you want to include some prior information. The posterior, at first the posterior is just a collection of samples of model parameters. But with these, you can go on and derive other quantities from it. You can make predictions, you can calculate R squared, you can compare different predictions of different groups or whatever. And all you do there will be a distribution. And that's a good thing, because this means we always can assign probabilities to research questions. And again, please always use the full posterior. Do not just extract mean parameter values and use them for making predictions. Again, a couple of literature here. This is not only textbooks. There's a couple of papers about prior choices and prior predictive checks, and they are all ecology related. Okay, data per parameter. That's a good question. So there are some rules of thumb of how many data points you should have per predictor, right, in frequency statistics. The reason for that is in frequentist statistics, or one of the reasons is confidence intervals and also p-values are only kind of correct if you have a couple of data points. They all rely on some normality assumption, and this is only guaranteed for a certain amount of data points. So the measures of uncertainty in frequentist statistics are usually not to be trusted if you just have very, very small amount of data. Bayesian statistics, however, does not have any limitations here. No matter how small your data set is, you will always get the correct quantification of uncertainty. That doesn't mean that you will find an effect. Small data sets produce a wide range of uncertainty. That's just how, due to the nature of the math behind it. However, the uncertainty you quantify will be correct. You can trust it. So that's one case where Bayesian statistics really is of advantage if you have small data sets. In small data sets, Bayesian statistics will quantify your uncertainty correctly. The other part of the question is related to computation time. I would say often they scale not too badly with the number of data points. However, I think more the number of parameters can be a bottleneck, but I don't have a good answer there. You have to just have to check it out. If the runtime gets too high on your computer, you can move to a cluster. However, moving to a cluster, you will not get a benefit from having like 100 CPUs. You can parallelize or run each chain on one CPU. However, usually each chain can only exploit one CPU, and it doesn't scale well with using more CPUs. So often having a cluster, you won't be able to use hundreds of cores, because the MCMC, they just have to go through every sample, and this usually uses one core only. Okay, so we continue with prior and posterior distributions in BRMS. This time we are working with an actual data set. And I load these packages. I think we need all of them. So the EcoStats package is, I think, from David Wharton's book. I think it's a frequentist book, but this package contains some nice data sets we can also use. So we are loading this data set, which is from this package, and we have 130 observations with lots of variables here, but we are interested only in a couple of things here. And this is the latitudinal gradient of plant height. So we are only interested here for now in two variables. This is latitude as a predictor and plant height as the response here. And I'm log transforming this, the response. And for this relationship, we want to estimate if there's a connection. Right, so if on average there is a decrease in plant height with latitude, and we can fit a very simple linear model to that. Note this is that might not be the best model here, right? So many other factors would go in there. Just fitting plant height versus latitude. We are missing a couple of predictors here. But for trying posterior and prior predictions and so on, this is a nice data set. Okay, so first the model we are fitting is log height versus latitude. First of all, yeah, the model description. So log height, I use the log transform of the response here directly as a response. Deterministic model is just depending on latitude, so linear regression. And we assume a normal distribution of log height around the mean prediction. We can transform the predictor before fitting the model, or we can just use log height here, then the predictor is automatically transformed. Let's say we have some information from another study from before. This is a prior on an effect and the effect of latitude. So here we are specifying a prior, which is a normal distribution, which has a mean negative value and some standard deviation, small standard deviation, because we assume, or we have some other evidence from other observational studies that this association is negative. Because there was a question before about computation. So the default number of chains is 4, but you can also specify this. And by specifying cores equal to 4, I say I'm using 4 CPUs. And this means that here all the chains are run in parallel. So I don't have to wait that long. And this is a most convenient way of speeding up your computation, because nowadays almost all the laptops have more than one CPU and we can use them. Yeah, thinning used to be more important in other environments, like for instance JAX, because other algorithms had the problem that the chains had a lot of autocorrelation. So you would see some up and down in your chains with a lot of kind of still wiggling around, but still chains like wandering around. So you would have to use long chains, maybe 100,000 samples to get this kind of fuzzy caterpillar behavior. Yeah, and then if you don't want to use have your big matrix with 100,000 entries, you can thin this and just save every 10 samples, and then you just have 10,000 entries, which still is a lot. However, with Stan, and BRMS uses Stan, this is not so much important anymore, because the algorithm is so efficient that you usually don't have to run chains that long, and the autocorrelation of each chain is very low, and you can use all your samples without just saving every 10th or every 20th of these samples. So in Stan and BRMS, this is not thinning, as you can do it just by specifying, I think, thin equal something, but usually you don't have to. Okay, oh, it was so quick that I didn't see what happened. Let's run this again. Okay, yeah, this is really quick, and here all the chains are actually run at the same time in parallel, because I specified core is equal to. And if your MCMC takes, I don't know, 10 minutes to run, then you only have to wait 10 minutes instead of 40 minutes, because all of the 4 chains are done simultaneously. Okay, we get no warnings. That's the first good sign. But we always look at the convergence, both looking at the model fit and see if we see the fuzzy caterpillar here. That's fine. So all the 4 chains kind of behave similarly. And also we look at some quantitative measures. So for each parameter here, 3 parameters, we get this R hat value. That's the important one. This basically tells me the same thing. Did all the chains behave similarly? If this value is close to 1, it's usually larger than 1, but here to the second digit, it is equal to 1. This means all the chains kind of behave similarly. And also the both measures for effective sample size are in the same order of magnitude as the total number of draws here. So we are confident that the MCMC converged. Okay, now first step, okay, MCMC converged. Second step, we can look at if this is a good model, but we can always check this with the conditional effects here just to see, yeah, to have a first look at how the model and the data match up. I added this part here to look at, so the MCMC dense, gives you a density plot. So this is a histogram, but you can also use a density plot. It doesn't matter that much. But because BRMS doesn't have a function to plot prior and posterior in one picture, I added this little part of code to display the prior and the posterior, just to give you an idea, how they both match up. Right, so this is the posterior. This comes from the model fit, and the light blue one here, this I added manually here by using the geom function. Here I plot the d norm, so the density function of the normal distribution with this mean and the standard deviation, and these are the mean and the standard deviation, which I chose for the prior distribution. Usually, you would check your priors, or you would make prior predictive checks before model fitting, right? Because you first check if your priors are good and then, or meaningful, and then you fit the model. However, I will do this later because I will go through the steps of model predictions, and then it's easier in the end to understand what prior model predictions are. So usually with prior predictive checks first, but we will do them later to see how the predictions are generated. Mm-hmm. So we are kind of repeating parts of the step we have described in the lecture already. You can extract the samples in the form of a data frame or in the form of a matrix. We've seen that the posterior distribution is a multivariate object. So we can also plot this in a more multivariate way, for instance, with a pairs command. So this gives you on the diagonal here, that's the classical histograms. But on the off diagonals here, you see the pairwise plots of parameter 1 versus parameter 2. For instance, here intercept versus slope. Since this is usually not, you can't see much there, you can also specify this here with the off diagonal function that you see here. This is a density, so dark shades mean higher concentration of samples and light shades mean a lower concentration of samples. And here we see this classical negative correlation of intercept and slope, because when the intercept changes, when the slope changes, simultaneously here the kind of intercept changes. But this is perfectly normal. So a bit of kind of correlation in your parameters is totally fine. However, internally, BRMS doesn't use the intercept, but it uses the intercept for mean-centered variable. And by mean centering, you remove this correlation between intercept and slope, because the intercept is now happening in the middle of the data. And then the slope change doesn't affect the intercept. However, this is just done internally, because then the samples can be generated more effectively, or new samples can be generated more effectively. But the true parameter here, the parameter this is used for output, this is the B_intercept. And they are a bit correlated, but that's not a problem. However, be aware that, yeah, the posterior distribution is actually multivariate. And here, large values of slope correspond to smaller values of intercept. And that's another reason for always using the whole posterior for predictions and not just means of the single parameters. Yeah, what are we doing now? Okay, let's do some predictions. So the posterior here, again, it's a matrix. And each row in this matrix corresponds to one regression line. We check the conditional effects plot once more. You can also change the level of your confidence intervals here with a probability statement. But we can look at the single regression lines here with these comments. So if you specify spaghetti equal true, then you get a spaghetti plot. Means that each of these lines here is now one regression line generated from one sample. And yeah, I would specify the number of draws. So it randomly selects 100 samples, because if you plot 4,000 regression lines here in this ggplot, I think my computer will freeze. So here you can specify just the number of random draws in the samples, just to give you an idea that these confidence intervals are actually generated from all of these different regression lines. Okay, but they all just use the deterministic part of the model, right? So the regression line only contains intercept and slope, but we know that the statistical model also contains a standard deviation, how strong the data deviates from this mean regression line. And you can visualize this also with the conditional effects by specifying the method here, which is posterior predict. This means that additionally to the deterministic prediction or the fitted value, it automatically includes the standard deviation. And then, yeah, you get the full uncertainty here in the data prediction model. And as usual, a couple of data points are outside this 95% prediction interval, but roughly 95% of the data are inside here. Okay, this is just plotting prediction intervals, but usually if you, for instance, want to compute R² value or some other measures, observed versus predicted, you have to make predictions for each single data point. And you can make this with a fitted command or with a predict command. So the fitted command gives you kind of fitted values for each of the data points. So here you have 130 data points. For each of them, you will generate a prediction. Here, this is the mean prediction, and here's the standard deviation. However, this is the fitted, so it just uses the regression part, so just the linear part, and not the model uncertainty. Sorry, not the residual uncertainty, whereas the predict part also includes the residual uncertainty, and you see that here the estimation error, so the standard deviation here is kind of low, and the standard deviation part here is higher because it also includes the residual uncertainty. So if you do not specify anything else here, it just gives you predictions for all of the data points. But let's say I want to make predictions for a certain value of the predictor. Here, for instance, what is the mean predictions at latitude equals 60? Then I can specify this. I have to hand over the variable new data, and here I generate a data frame with just one entry, latitude equals 60. So here we, this is the fitted. So this is just the mean regression line. So it should be here at 60 and some standard error, which is kind of small because it is, actually it comes from this one. So this is that uncertainty here. And the other one, that's the predicted. It additionally includes the uncertainty of the residual. So the mean regression here is the same, or almost approximately the same, should be the same, up to yeah, some digits. But the estimation error here in this case, the uncertainty is much higher. Yeah, usually we want to make inference on the model. For instance, on the question, is the slope negative? Then here, for instance, you can just ask this question, is the slope negative? And this directly comes from the distribution or the posterior distribution of this one parameter. And so this corresponds to this distribution of this parameter here. So the mean estimate for slope is minus 0.04. And we have some 95% quantiles, which are between minus 0.06 and minus 0.03. So the whole distribution has, all the quantiles are smaller than 0. But if you want to quantify the actual probability, again, we get here the mean, the confidence intervals. So we get a probability here. In this case, the probability is 1. So the whole distribution or the whole distribution mass is smaller than 0. You can also look at the plot again. So here, this is this distribution, and you see that the whole kind of probability mass is negative. So here we are actually very confident that the slope actually is negative. But that's not the only thing you can do with the posterior predictions, or in this case, we didn't even need to do a prediction, we just looked at the slope. So often your hypothesis or the statistical inference can be attributed to just one parameter, and then you just calculate probabilities for this parameter. But often your hypotheses also are about predictions. And we can also compare predictions and assign probabilities there. For instance, if you're interested in what is the average difference in mean height between 40 degrees latitude and 60 degrees latitude. Or rather, yeah, here in this plot. What is the average difference between 40 degrees latitude and 60 degrees latitude, and also the associated uncertainty there? So you could make predictions, in this case, the fitted values. And then we get, yeah, some estimates. Okay, the one is larger than the other, and both of them are associated with some standard error. However, this is not enough, right? We only know, okay, that's the mean prediction here at 40 with some error, and that's the mean prediction here at 60 with some error. But what you actually need is a distribution of the difference there. And here you can yeah, make predictions of their difference. So if you execute this, you get a summary here, right? So not the whole distribution, but you can also get the full distribution, I think, by saying summary equal false. Yeah, then you get the whole distribution of your fitted values for all the samples. Or you can use another function, which is called posterior epred. That's actually doing the same. Yeah, it's the same. So we can either use the fitted and specify summary equal false to get all the samples, or we use the posterior epred function for both of them. And what is now important here is that so the first column is the predictions for latitude 40. The second column is the predictions for latitude 60. The important thing is now that each column is generated with the same posterior samples, right? With the same posterior samples in the parameters. So you can actually make row-wise differences now. And then you will get a distribution of the difference. So that's the distribution of the plant height at latitude 40. That's the distribution at latitude 60. And you can make a distribution at the difference. You can just subtract them from each other. So both of them are vectors of the same length. Each of the entries corresponds to the same sample. That's important. So you get the distribution of the difference here. And yeah, with everything you compute from the posterior samples or from the predictions, with all of them you can make statistics. So you can plot the histogram, or you can extract the mean of this difference, which is 0 dot something, and also its standard deviation. So it's uncertainty. Or for instance, quantiles. And here you see that the quantile of the difference does not cover 0. So we are pretty sure that the difference, that there is a difference between plant height at 40 and 60 degrees latitude. If you want to calculate the probability, you just have to count. But also we can use a fancy brms function, but you can also just count. So by specifying mu40 larger than mu60, you get a vector of true or false. So this is true whenever this condition is satisfied. And if you sum them up, summing up all the true values, every true is interpreted as 1, and every zero is interpreted, every true is interpreted as 1, every false is interpreted as 0. And if you sum them up and divide by the length, you get the proportion of, or you get the probability of mu40 being larger than mu60. In this case, it is 1 because all the samples of this difference is positive. You can also use a brms function for this. Took me a while to find out how this works, but it does. So the trick is that you have to put them in a named matrix or in a named data frame. So for instance, with the fitted command here, I make predictions both at latitude 40 and 60. I have to have it as a data frame, and I must assign names to it. And then I can use this with a hypothesis function. So we used the hypothesis function before to calculate probabilities of parameters, but you can also compute probabilities from everything you derive from the parameters. It just has to be coded in this kind of matrix form where each column corresponds to a certain prediction and each line corresponds to one sample. And then you can put this into the hypothesis function and ask the question, okay, is plant height at latitude 40 larger than plant height at latitude 60? And I get the same answer. The probability here is 1. You can also plot this. And again, you get a distribution of the difference here. And this, I think, is really helpful for many questions. Whenever you can translate your research question into something you can derive from the data, for instance, and a difference in predictions or whatever, you can just calculate them, keeping in mind that everything is a distribution, and then using this distribution to assign probabilities to to statements like is the latitude, is the plant height at 40 larger than at 60? And this is kind of, you can do all kinds of stuff there. If your research question is a bit more complicated than just comparing two predictions, but doing anything else to these predictions, you can always translate this into something you can for which you can calculate the probability here. Okay. I already went ahead a bit. I did statistical inference already, just to show you what you can do with the posterior predictions. But usually the workflow is as follows. You should first think about your priors, maybe do prior predictive checks, then fit the model, check the convergence, then check the posterior predictions if the data and the model match up nicely, and only then you can do model inference. We didn't cover everything yet, so I'm talking in the last, let's say, 10 minutes about posterior and also prior predictive checks. So after model fitting, you would be interested in, is your model and your data, are they matching up nicely? And you can calculate, for instance, the R-squared value. Here in this case, it's not too high, but in ecology, we are used to that, having the amount of explained variation, for instance, around 20%. That's the same interpretation as in frequentist statistics. But since everything is a distribution, we also get some associated uncertainty here. That's how much of this variation here in the data is explained by my model here, and the answer is here around 20%. If you're talking about the posterior, we only have access to the posterior in form of a finite sample. So we only can plot densities, or we can plot histograms of it, and they are not always perfectly smooth. It does not mean that the actual posterior has multiple maxima. Usually, if you would increase the number of samples to a very high number, at some point you see that it is smoothly. Sometimes there are cases where you actually have kind of multimodality, where the posterior has like multiple peaks. But often, if your histogram just doesn't align 100% smoothly, that's nothing to worry about. Okay, so this is one quantitative measure of checking how well the model explains the data. There's also two graphical tools, and that's the posterior predictive checks function. First, this one here. Maybe this was what you were talking about. Okay, I see. Okay, we see here, again, that's the histogram of the data, and definitely, yes, I'm seeing a dip here. But remember, the data itself, the raw data, the response, there's no need for it to be normally distributed. There's no assumption that the data itself has to be normally distributed. All right, so there's no assumptions that here the y-axis, the values on the y-axis have to be perfectly normally distributed. And that's what we are seeing here. All right, so there's some part in the around, let's say around 2, where we have less values. Maybe you can see it here. Yeah, okay, here there's maybe here around 2, there's a bit less values than here and here. So it's usually not a problem that this just comes from the data. However, we are seeing here that this property is not represented by the model. So the model usually does not recover this histogram of the data. And usually this could be explained maybe by a missing predictor. So maybe we have missed an important predictor here. We just regressed height versus latitude. We didn't include rainfall. We didn't include temperature, whatever. So this could be an indicator that maybe we have to improve the model. The second check is the observed versus predicted plot. And we see generally here quite a lot of spread. However, I don't see any kind of structure here so far, so I wouldn't say this is too bad. Note that this conditional plot, I mean, you can do it if you have multiple predictors, but if you have multiple predictors, you always should also look at the observed versus predicted plot, because on both axes, you see the response values, the observed responses and the predicted response. And this works no matter how many predictors are involved. So that's the kind of classical things I would check with some functions from the BRMS package. But nowadays we have the performance package, which works quite nicely, at least for linear models in BRMS. And you get all these model analysis in one plot here. And these are the classical ones you should look out for, especially linear models. Again, yeah, it doesn't look too perfectly here. I mean, this should be flat and you see an S shape, but I guess this is also maybe just because there's not many observations here in this range. And here the plot could be nicer, lining up more nicely here. So maybe just using one predictor isn't enough here to explain the variation in the data nicely. Okay, so we learned how we can perform predictive checks with the model, with the posterior. And you can also do this before fitting the actual model, just with predictions from the prior, to see if predictions from the prior are in line with your data. And this is prior predictive checks. And you can use the same tools here as you would do with posterior predictive checks. So let's look at the priors we used here. This was the model, right? So we had some prior for the intercept, some for the sigma, and we assigned the prior ourselves for the slope. And for this model, you can also sample from the prior and make predictions from the prior by here adding this line, sample prior only. Then you can fit the model. I mean, you don't necessarily have to look at the summary and not look at the fuzzy caterpillar plot because you're just sampling from the prior. This usually shouldn't be an issue at all. But the cool thing is now you have this fitted BRMS object that just contains samples from the prior, and you can use this for all the other BRMS functions. So you can use conditional effects plot here. All right, so this is samples from the prior, and only the deterministic part, and it already covers the data quite nicely. if you look at the spaghetti plot, you see single regression lines, which also cover the data quite nicely. So, so at least your prior isn't completely completely off. You could think of maybe tightening the priors a bit, right, to shrink the range here of predictions or fitted regression lines. You can also do the prior predictive check here, right? And there you see, okay, well, yeah, this is the same histogram as before, just zoomed out. And then you see the data sets predicted prior, and this, I would say it's okay. You can decrease the variation a bit to tighten the sampling space a bit. But I wouldn't say it's super critical here. So in this case, what did we have here? Okay, yeah, the intercept for the intercept prior had some standard deviation here, and I took the same here, but I decreased the standard deviation from 2.5 to 1 to decrease the variation a bit. Otherwise, everything is the same here. And then we can check if this had an effect. So if you look at a conditional effects plot, okay, the regression lines now match up with the data a little bit better. Okay, there's some outliers, that's not a big issue. But altogether, I would say that's fine now. I think it's also would have the other one would also have been fine. Looking at this again, and I think it matches up a bit more tightly. So that's fine. And then I would fit the model with the new prior. Yeah, go on with my model analysis. Okay. I must say the order of things we did here was a bit all over the place because first wanted to introduce, okay, what is the posterior? How does it look like? How do I make predictions? But as an exercise for you, I want you to analyze another data set, but now in the correct order. Okay, there will be a new data set, water quality. So here we have water quality in streams. So this is the response depending on the catchment area. So the larger the catchment area, the further downstream in the river, the water quality was measured. And simple linear regression model as well to check, yeah, if you're further downstream or further upstream, how this impacts the water quality. And I want you to do this in the correct order this time. So you can, for instance, scale the predictor to make everything a bit more manageable. Look at different prior choices, make prior predictive checks, fit the model, check convergence, check the model fit. And then, I mean, sure, we see, okay, probably the effect is negative, right? You see this already here, but I guess with the hypothesis, you can quantify this, but you can also check the difference in water quality between the mean, so somewhere here, so the mean and mean plus 1 standard deviation of the predictor. So this is the mean, and this is a bit further out, so this is a bit further downstream. And check if the difference of these predictions is meaningful, which means that it is kind of non-negative. Sorry, it's negative or positive, so it's not zero. Yeah, I think you can just mostly copy and paste parts of the other script, but put it in the correct order. And this is the actual steps of an analysis you would do to answer these questions about river health and catchment area.